welcome back. This is Technical Prelim 3. Today we are going to talk about calculus tools in Mathematica. We are going to talk about how to do differentiation, how to do integration, and how to solve differential equations in Mathematica. So let's go ahead and get started. Let's say we want to find the derivative of a function, and let's say the function is log of x over x. I can simply use a built-in function called d and write down my function, which is log of x. Let's just start with log of x. I want to differentiate with respect to x. We know the answer. The answer is 1 over x. So let's go ahead and execute this, and this is going to give me 1 over x. So d is the derivative function, and you can try it out for other examples. I can say x log x, and I want to do first derivative of that. That's going to give me 1 plus log x. Let's go back to log x for a moment, and let's say we want to find, this was the first derivative. Let's say we want to find also its second derivative. Then for second derivative we have to simply add a flower bracket around x, and say we want the second derivative, and that's going to give me minus 1 by x squared. If I put back 1 over here, I'm going to get 1 over x. By default, if you just provide what variable you want to differentiate with, it's going to give you the first derivative. If you want nth derivative, you just provide the value of n over here, and that's going to give you 2 by x cubed. If I put something that is not defined and just write n over there, it's just going to give me, it is going to apply some of the rules, and if it can solve, it's going to give me still an answer. In this case, it says that if n is greater than 1, then I get this particular object, and otherwise it's just going to give me log x back. So you have to use this with a little bit of care. Let's go ahead and change this back to 2, and we can go ahead and try the third derivative, and so on. Let's go back and say we want to find out first derivative log x over x. So let's say d of log x over x, and I want to get its first derivative. So I'm going to write that, and I'm going to execute, and I get 1 minus 1 by plus 1 by x squared minus log x by x squared. Let's say we want to find out where does this function log x over x has a minima. Let's go ahead and plot it first. So let me go ahead and plot log x over x. X goes from 0 to 4, let's say, and we get some function like that. Okay, let's go ahead and make it slightly larger range, maybe 10, and we get something like that. And I think it's not printing the negative range, so let me put plot range from -1 to 1, and there we go. So somewhere this has got a maximum or a minima. It's got a maximum somewhere around here, and I want to find out what is that, what is exactly that number. So to do that, I have to take derivative of x and set it to 0, derivative of the function and set it to 0. So the function is log x by x, so I take derivative of that. Now I get this quantity. I have to set this to 0, and then I have to solve for it. So to do that, what we'll do is we'll set it to 0 by using equal function or double equal to. So double equal to is a comparison which says that we're going to set it to 0, and that just gives me an equation. What I want to do is I want to solve for this equation. For that, I'm going to use a function called solve. Solve is again a built-in function to solve, for example, polynomial equations or finding zeros or solving for set of equations. So let's go ahead and do this. And I need to specify, but what do I want to solve for? I want to solve for x over here, and when I do that, it gives me a solution that x is e. Notice that this solution is in form of a replacement rule. The first flower bracket says what is the set of solution, and second flower bracket is for if there are more than one solutions. Let me give you another example of solve to make this clear. In this case, you can simply take a quadratic equation. So let's say 2x squared plus 2x minus 1, and we'll say solve for x. Sorry, you have to specify this as the equation. So remember, you have to put a double equal to. With a single equal to, you'll run into some sort of error. So let's go ahead and execute that, and there you go, it gives you two solutions. Each sort of solution is going to give you one set of will be in one set of flower brackets, another solution will be in the other set of flower brackets, and all these both these solutions are put together in the outermost flower bracket. If I want to particularly extract a solution, all I have to do is, let me assign this to a variable, let me call that variable solve, execute it, and then when I say solve 1, I get the first solution. Notice that I'm using double square bracket here because I want to read the first element of this list. I want to extract the first element of this list, which is this guy, and for that I'm going to use double square bracket. Single square brackets are used for arguments. If I do solve 1, I'll just get solution, the solve itself, and it'll just append 1 after that because it doesn't know what to do with this one. But with the double square bracket, it's going to extract me the first element of that list or that array, and that's the first solution, and I can do the same thing for the second solution. How do I extract exactly this piece out? Well, you can copy and paste, but if you are writing a code, you want to extract this out through a code, and to do that, what we do is, we've already got this part, we simply say x/dot solve 1, and that will give me the solution. Notice that solve 1 or solve 2, these are replacement rules, and I can apply these replacement rules to any expression that I have. In this case, my expression was simply x, and when I applied that, it just substituted x by the value that solve 1 was providing, so I just got that. But you may be interested, for example, in getting back your equation, and you want back your quadratic polynomial, and you want to say, I want to evaluate this polynomial at the the first root, and what do you expect? You expect to get a 0, so I can say I am going to apply this at first root, and it gives me some expression. Let me go ahead and expand it out by doing simplify, and that gives me 0. And this was expected because this was a root of the equation, and I can try the same thing with solve 2, and that also gives me 0. So this is how you extract the solution. Solutions are in form of replacement rules. I can extract a specific solution, apply that to any expression that I want to check what result I get. Coming back to this equation again, what did we do here? First, we constructed the equation by taking the derivative of log x by x equated to 0, and once we have got that, we asked to solve for x, and that gave us the result. X is replaced by e. E is simply the Euler number, close to 2.718. If you want to check it out, I can go ahead and in the same line of code, I can simply say x/dot that. I'm going to execute that, and it's going to give me e, and if I apply /n after that, I'm going to get 2.71828. // is postfix operator. It says that everything that is preceding to this, apply the numerical function, and that gives me the number 2.718, which is nothing but the Euler number. So this was a quick look at finding out derivatives using D, and finding out the minimas, maximas, and extremas using the solve function. You can also do integration using Mathematica, and I'm going to demonstrate to you now how to do that. There are two ways to do integration. One is the analytical way of doing an integration. So for that, we've got built-in function called integrate, and if I provide it a function, let's go ahead and provide it log x by x, and we'll say integrate with respect to x. It's going to give me a result, which is what we usually know as the integration. The result is log x squared by 2 and up to a constant. So this gives me a result up to a constant, and if I can do a definite integral also by supplying a range for x. Let me do this in a separate line. I can supply a range for x by saying, as always, x goes from let's say 1 to 2, and the answer I get is simply log 2 square by 2. You can validate it through analytical methods that this is actually the right result. Let's go ahead and do it from 0 to 2 to see what happens. It complains, it says that integral log x over x does not converge on 0 to 2, and that is true. If you look at the plot over here, for x less than 1, this is negative and it's diverging, and if you try to do the integration in the 0 to 1 range, it's not going to give you anything finite, and that's what this integral complains about. So let's go back and set this limit from 1 to 2. So this is doing analytical integrals, indefinite analytical integrals. This is definite analytical integrals, and you can also do this for something else like y over here. Doesn't have to be so the specification that we have provided over here, we're telling integrate with respect to x. So for that, as far as this integral is concerned, y is just a constant, and I can go ahead and execute this, and I'm going to get y is going to be treated as a constant, and I simply get half of log xy square. If I want to integrate this to y also, you can simply add y as another variable and go ahead and calculate that, and you get indefinite integral for log xy by x integrated with respect to x and y. And you can do this also with definite integrals. So I can go ahead and put a range for y also, y from 1 to 2, and there we go. It did a definite integral by substituting the limits. So this is integrate. Similarly, for differentiation also, you can provide other terms or other parameters in there, and they'll all be treated as simply as constants. Let's go ahead and look at numerical integration. In cases when you cannot evaluate analytical integral, you can do numerical integration. Let's go ahead and try a function where we cannot get a numerical integral. Let's say 1 plus analytical integral. So let's say 1 plus t square. I'm not sure if there's an analytical integral for this, but let's find out if Mathematica has a solution, analytical solution for this. It does. So let's go ahead and maybe find another one. Okay, let's just try with this. So this is analytical integral. Let's go ahead and give it a range from t goes from 0 to 1, and this gives me a definite integral, and I can actually go ahead and compute its numerical value to see what I get. That's a numerical result. Let's go ahead and try this with a built-in Mathematica's built-in numerical integration method, that is NIntegrate. That's NIntegrate, and let's provide the same set of arguments to NIntegrate. And we are going to simply execute that, and wonderfully we get the same result. Not surprisingly, of course, this was a simple function. We knew the analytical answer for this result thanks to Mathematica's built-in library of functions. It gave us analytical result for integration of this function, and NIntegrate also yields me the same result. I would recommend that you explore both integrate and NIntegrate, look at the options, look at the documentation, look at it in what various ways you can use NIntegrate. You can also do NIntegrate in multiple variables. Let's also explore that really quickly here, and I'm going to add something of that sort. Now actually this is 1 plus at plus t square. If I try to call NIntegrate with that, it's not going to work, because NIntegrate doesn't know what is the value of a, and it's not a numerical value, so it cannot apply a numerical integration. So it's going to complain the integrand given by this expression has evaluated to non-numerical values for all sampling points in the region with boundaries 0, 1. So it says that in your specified range of variable t, the range 0 1, this integrand does not evaluate to any numerical value, so therefore it cannot actually do numerical integration. So therefore we have to provide a value for a. If I want to do something of that sort, the best way to do that is define a function f of a with a colon equal to, which is the set delayed operator. It says that I'm defining a as this function, but I'm not going to evaluate it right now. I'll evaluate at a later stage. So I'm going to go ahead and define that. Now I can call the f with some value, let's say f with 1, and the answer is 0.767. You can go ahead and try out f with 2 and f with 3 and so on. If I wanted to make a plot of f of a with respect to, with a going from really small value 0 to 1, we can make that plot, and what we see here is that it has a function that decreases. So this numerical integration as a function of a drops down. All right, very good. So this is numerical integration. Let's go ahead and move on to solving differential equations. So for that, I'm going to solving differential equations. I'm going to introduce one more inbuilt function called DSolve. DSolve stands for solving differential equations. D is for differential, and solve is solve was used for solving polynomial equations or linear equations or for functions. DSolve is for solving differential equations. So let's see how this works. Let's say we're interested in solving the equation x dot equal to minus 2x. Okay, so let's go ahead and solve that equation. So to do that, it's understood that x dot minus 2x, I'm taking a derivative with respect to some variable. Let's say it's t, in this case it's time, so I'm going to say x prime of t, which means first derivative of x with respect to time with t, and I'm going to set that equal to, again I'll use double equal to symbol, and I'll set that equal to minus 2x, and I'm going to say give me a solution with respect to x. Now this is incorrect. The reason for this is incorrect is that I have not told what is this x. Is this x a function or is this x a symbol? What exactly it is, and it's going to complain. Let me show you that. It says that DSolve call with 2 arguments, 3 or more are expected. Okay, so what went wrong? Well, we should have said we should solve this differential equation with respect to what variable. So that variable is time t. So if we go and execute that now, this is still going to be wrong because it says the function x appears with no arguments. So here's x appearing, which is the function. It detects that x is a function because I've used x prime of t. So it doesn't like that. You have to provide the argument t, saying that x is actually a function of t. Let's go ahead and execute that, and there we go. Again we get a solution. The solution is again in form of a set of replacement rules. This is one replacement rule, and since only there's one solution, I only get one replacement rule, which is xt is e to the minus 2t times times unknown constant c1. We did not provide the boundary conditions, so it figured out there was some integration constant, and that integration constant is that this c1. Now this is exponentially decaying solution. We know that this is the equation for exponentially decaying solution, and this is indeed the correct solution. You can go ahead and check it out analytically yourself. What we'll do now is we will go ahead and make it a boundary value problem. To do that, what we'll do is, rather than providing one equation, we'll provide it a set of equations and ask it to solve all together, and boundary value conditions we are going to add as again equations. So let's fix the boundary condition here. Let's say this is x dot is e to the minus 2x, and we have already figured out the solution is x as a function of t is e to the minus 2t times a constant, and I want So x of t is some constant times e to the power minus 2t. In order to find the constant, I need some boundary conditions. So let's say at x equal to 0, x at t equal to 0 was 1, and then you can immediately follow from this that x of t, x of 0 is 1, so if x of 0 is simply c, which is 1, and therefore we establish that c is 1. Let's go ahead and do this automatically with DSolve. So we're going to go ahead and say x at 0. Remember that we're providing a boundary condition, so we say x at 0 is equal to 1, and it gives me e to the power minus 2t. It has found out that c1 has to be 1. You can try by changing it. If I make it 4, it's going to give me the constant as 4. So DSolve is quite capable of solving quite a few differential equations. In fact, it can solve a large class of differential equations. So let's go ahead and experiment a little bit more with this. We will use this for let's see if we can let's use this for solving a set of coupled differential equations. Let's go ahead and use x prime of t is minus y of t, and we'll say y of t is, or y prime of t is minus x of t, and let's remove this boundary condition for now, and let's go ahead and say that we want to solve for x of t and y of t with respect to t. There we go, we execute it, we get a solution, and there's again one solution, but there only one solution is there, but again this is a set of two equations, one for, or two replacement rule, one for x and one for y. Let me go ahead and give this a name, DSolve equal to this. So let's go ahead and see, this is x of t. The solution for x of t is that there are two integration constants c1 and c2, because there are two sets of first order differential equations. Again, those two constants c1 and c2 also appear for y of t. This is the solution for c1 and c2. And if you want to extract these solutions, we have to again say DSolve, and we have to say first, get me the first item, which is just the first set of solution that we have, and then we can say x of t slash dot DSolve, and that gives me this. And further, if I want, I can go ahead and say, you know, capital X of t is equal to that, and that will make a definition as capital X of t is that. Let's go ahead and supply a boundary condition. So you can supply a boundary condition here by saying x at 0 is 2 and y at 0 is 1. Let's go ahead and see what happens with that. There we go. Now that's my DSolve. I'll extract x of t from that, and this time I'm going to get x of t as that. I got it over here. I've defined x of t as this capital X of t. I'm now going to plot capital X of t, and to do that plot, I simply mention t goes from we solve it from 0 to 5, and let's see what the plot looks like. And similarly, we can also go ahead and do for y of t. You can say y of t is nothing but y of t slash dot is for replacement rule. This is the replacement rule that I'm applying. I execute that, and I get this is y of t. So let me go ahead and put x of t and y of t on the same plot to compare these two branches of solution, these two in two different directions. So that is x of t and y of t. So that was Mathematica's built-in function for solving differential equations using DSolve. Now this is an analytical approach. Mathematica gives you an analytical solution for a set of differential equations and the boundary conditions. But there are examples where we can actually not use DSolve and we have to resort to some numerical method. Let me give an example. So let's try DSolve for some equation, let's say x prime prime of t. So x double dot of t is let's say minus x. We know this is the equation for a harmonic oscillator, and we know the solutions of this are cos t and sin t. Let's go ahead and check it out. So if we have to say x of t, and we say that I want to solve for x of t as a function of t. Oh, there you go. I made a mistake. It has to be equal to. I have to go ahead and clear x. I have to actually go ahead and clear x prime of t, I think. Okay, when that happens, the only way is to clear everything. So let me go ahead and global star that will clear everything from the context. Let's go ahead and try now. Still doesn't work. Okay, let me go ahead and make this change the variable here. There we go. So that happened because I accidentally used equal to rather than double equal to, and something goes in the context that gets defined and Mathematica doesn't like it. If it happens with you, don't panic. Just clear up the memory, close the file, close the Mathematica and reload the file, or change the variable just like the way I did if that happens to you. So now when I solve this, I get the solution C1 cos t plus C2 sin t. You all know that this is the general solution for a simple harmonic oscillator. But let me go ahead and add a term to this. Let's say I am going to add y of t to the power square. Let's do y of t square and go ahead and try to solve this. It can actually, it appears that it has solved it, but this solution is not really useful because see, this solution is packed inside the solve function itself. So it says that it has got some idea of the solution. It says that the solution is given by all of this nasty stuff. If a solution is given by solving this equation, and you have to, if you can solve this set of equations, you have the solution for y of t. Now that's not very helpful, but otherwise this is not making much sense, and in this kind of case we'll probably want to get a numerical solution. In that case we'll resort to rather than DSolve, we'll resort to NDSolve, which is the numerical method for solving differential equations. Now NDSolve can solve a whole lot of differential equations, but maybe not everything. But in any case, what we'll do is we'll go and explore NDSolve for this particular problem. So the function is simply NDSolve, like I've shown you over here. But NDSolve doesn't work if I don't give a boundary condition. I have to give initial value conditions or boundary conditions for NDSolve to work, just like NIntegrate doesn't work for doing indefinite integrals. NDSolve doesn't work to solving indefinite differential equations without any boundary conditions. In order to provide boundary conditions, I must provide some more equations, and for that I'm going to go ahead and say yt y at 0, that is at t equal to 0 is, let's say it's some amplitude 1, and since this is a second order differential equation, I have to provide one more boundary condition, and this time it will be y prime of 0, that is the first derivative of y at 0. Let me go ahead and call it 0. So essentially what I'm doing here is I am this is an oscillator, this is an anharmonic oscillator. I'm saying that you take my anharmonic oscillator, set it at t equal to 0, set it to some amplitude 1, and speed 0 or y dot equal to 0. So that's like setting the pendulum or your anharmonic oscillator to the maximum amplitude and releasing it. So let's go ahead and try that. We may have to also say for what time range. Okay, let's go ahead and try that. Just like that should complain. It says the range specification t is not a form of the form some range for t. Okay, so we want to provide some range for t. Let's go ahead and say t goes from 0 to 5, and let's go ahead and execute that. There we go. It gives me some expression. It's unclear what that result is. It's in some sort of interpolating function, but if you see this, don't panic. The important thing to note here is that this is still a replacement rule, and y of t is some inbuilt numerical function that Mathematica is providing. We'll learn how to extract this out and plot it. So here is again one single solution it is found, and let's go ahead and extract this out. So let me call this as DSolve as my solution. I'm going to go ahead and execute that, and I'm going to say DSolve 1, which is simply going to give me the replacement rule. Now I'll say y of t applied to DSolve gives me this function. Again, I want to do what I did some time back. I want to define y of capital Y of t as a function. I'll say this is equal to that and execute it. Now capital Y of t is an ordinary function for me, which I can go ahead and use like ordinary function and plot it. So t goes from 0 to 5, and that gives me just a constant line. So that didn't give me anything interesting. Let me go back and change something about it. Let me go ahead and make it cube and try this out. Again, seems to be giving me a flat line. Okay, let's try something else. Let's try a damped harmonic oscillator. So let me put this as minus y prime of t, and there we go. That looks something interesting. And there we go. This is a damped harmonic oscillator. If we make the damping term really small, you should be able to see many oscillations happening. And let's go ahead and increase the frequency. Let's make it 4, and there we go. And now the damping is probably too slow, so let's increase it slightly so that we see a nice damped oscillator. Okay, maybe a little bit more. There we go. We have a nice damped oscillator. We can try and go ahead and say what happens. See, we solved it only up to t equal to 5, but let's go ahead and extend it out to 10, and you see when we do that up to 5 it gives me a reasonable solution, but then it diverges at 10 because we asked DSolve to only solve between t from 0 to 5. It only gave me an accurate solution between t equal to 0 and 5. If I increase this to 10, you'll see how the result will change, and there we go. And that's the solution of a damped harmonic oscillator using a numerical method of doing NDSolve. This equation is analytically solvable, and we will do this in one of the lectures. But let's take an example where this is not analytically solvable, and that happens when I put a frictional term. For example, if I put in some other term, let me go ahead and put in the yt as well, and that is probably not analytically solvable, but let's go ahead and see what happens over there. This is some strange behavior. Nevertheless, let's make it square. It's probably doing some restoration, and there you go. There's some damping. So this is some sort of damping term where damping is opposite to velocity, but with a y squared arm. You can increase the damping, and that should make the amplitude go down faster. So this was introduction to calculus tools built into Mathematica. Let's do a quick overview. We talked about derivatives. We talked about higher order derivatives. You can also do derivatives with respect to multiple variables. For example, let's go ahead and check out this one more example. Let's say this is log of x and log of y, and I want to find derivative with respect to x and y. I can simply say third derivative with respect to x and second derivative with respect to y, and that will give me the corresponding result. And you can cross check analytically that this is actually correct. So we talked about derivatives. We talked about integral, definite and indefinite integrals. Then we talked about numerical integration method, and then solving differential equations both analytically using DSolve and numerically using NDSolve. We'll use some of these functions as we go ahead and progress in this course. We'll see you in the next video.